This is a particle filter question, where we start with a single particle over here facing east. That particle has an x, a y, and a heading direction. And this particle lives on a checkerboard with black squares and white squares. Let's assume we draw 5 new particles from this particle for the motion of going right. And they end up as indicated over here. Each of these 5 new particles, one of which falling into A2, 2 of which falling into B2, 1 into C2, and 1 into B3, each of these particles will obtain an importance weight as now the robot measures it's on a black square. The measurement is black. To calculate the importance weight, let me tell you the probability of seeing black on a black square equals 0.8, whereas the probability of seeing black on a white square is only 0.1. So I want you to tell me the total importance weight that fall into A2. Here we just have a single particle. Into B2, please add the importance weights of both particles, C2 and B3. Please add your numbers over here. In resampling in the next motion step, let's assume the following 3 particles are used, where the other ones are being ignored. 2 of them live in B2, 1 in C2. The robot again moves right, and we get particles that distribute as follows. 2 fall into B3, 2 into B4, and 1 in C4. So using the same measurement properties as before, and now a measurement of a white square, tell me what the cumulative importance weight for the 3 new squares is, where 2 of the particles fall into B3, which happens to be a white square, 2 into B4, which happens to be a black square, and 1 into C4, which happens to be a white square again. Our robot Stanley performed as follows in the DARPA Grand Challenge in 2005. Came in 1st, 2nd, 3rd, or 4th or below in the ranking. In this final question, I'm going to quiz you about our approximate motion model for this robot, which I restate, and I'd like you to apply this exact motion model even over here, even though you might be suspicious of its accuracy. Suppose at time t equals 0, our coordinates are 0, 0, and 0 for all 3 variables. Delta t equals 4, I'm going to admit the units over here, v equals 10, and omega is p8, which is 22.5 degrees in degrees. Assuming we run one of these simulations exactly every 4 time steps, I would like to know what the robot state is after 4 of those updates, or put differently, total time of 16. So please tell me what x will be, y, and theta. Here's a sequence of MDP questions. We're given a maze environment with 8 fields, where we receive plus 100 over here and minus 100 in the corner over here. Our agent can go north, south, west, or east, but actions may fail at random. With probability p, and p is a number between 0 and 1, the action succeeds, and with 1 minus p, we go into a reverse. So for example, if we take the action go east in the state over here, with p probability, we find ourselves over there. With a 1 minus p, we find ourselves right over here in the exact opposite direction. So here's the east action again. With p, we go to the right. 1 minus p, we go to the left. Of course, if we bounce into a wall, we stay where we are. In my first question, I'll assume p equals 1. That is, there is no uncertainty in action outcome, and there's no failure. The state transition function is deterministic. I want you to fill in, for each state, the final value after running value iteration to completion. And please assume the cost is minus 4, and we use gamma equals 1 as a discount factor. So please fill in those missing 6 values over here. And the answer is obtained by looking at the nearest value minus 4, which gives us 96 over here, 92, 88, and 84. Let's now assume that p equals 0.8, which means actions fail with probability 0.2. And again, the cost is minus 4, and gamma equals 1. I want you to run exactly one value calculation for the state in red up here, assuming that the value function is initialized with 0 everywhere. what will be the value after a single backup of value iteration for the state up here? This is the state A4. And the answer is 76. The value over here is maximized for the south action, which we reach with 0.8 chance. With 0.2 chance, we'll stay in the same state for which the initial value was 0. And we subtract the action cost of 4, which is 80 plus 0 minus 4 is 76.